Good morning, everyone. My name is Trazz Pepper. I come from the University of Montana. This is a picture in the summer versus the winter, so we got a good amount of seasons there. I currently work at the University of Montana. I do work in the brain lab with Dr. Lucy Owen. Unfortunately, she did have or not unfortunately, but she did have a baby a couple years back, and due to the long travels to get here, she is unable to make it here with us today. So I will be giving the talk on her behalf. Alongside my lab members and I, we have been developing TimeCore. TimeCore is a Python toolbox that allows for the efficient calculation of higher order correlations beyond first, second, third, and all the way up to about 10. So TimeCore is a tool that's designed to find these higher order correlations in any time series data, not just fMRI data. But because we're at a neuroscience conference, I figured it's best to talk about its application to neuroscience data. The clearest way I have found to introduce higher order correlations is to discuss this diagram here. So we'll do a small brain for this example with only 4 regions, A, B, C, and D. Our 0th order correlation, or 0th order data, is just going to be the raw fMRI data seen there in order 0. Our 1st order correlation is going to be the correlation between those raw activity patterns. And the 2nd order correlation is going to follow from that and be the correlation, the Pearson correlations between those 1st order correlations. There we go. This brings us to the biggest problem with trying to calculate these higher order correlations, and that is exponential growth. So as every step we move up to calculate the next higher order correlation, our data doesn't just grow, it explodes actually. So to go from the 1st order correlation, we'll just have a smaller k by t matrix, which the k will be the number of brain regions and t will be the length of the time series or the fMRI series. And then to go to 1st order correlation, this is going to grow to a k squared by t matrix, and then to k to the 4 by t matrix, and et cetera, so on and so forth, as we move up these higher order correlations. So again, it makes calculating these higher order correlations beyond 2 really computationally intractable. As you guys have heard, some previous work has been done, oh my goodness, on those 1st order correlations, and then better yet, just on the 2nd order correlations, those dynamic edge correlations. But beyond 2nd order correlations, they have remained largely unexplored, and that kind of makes sense, as due to this, it's kind of computationally intractable to be able to calculate these higher order correlations. This challenge has motivated TimeCore, which has been developed by Dr. Lucy Owen and Dr. Jeremy Manning during her PhD at Dartmouth. And this allows for us to be able to go ahead and calculate those higher order correlations beyond 2nd order. So just for a little experiment, we were able to calculate up to the 15th higher order correlation using TimeCore. And to do that, the naive approach, you would need more bits than there is molecules in the university. Say what? Yeah, that's fine, yeah. So how are these higher order correlations calculated? So on the left here, we have a k by t matrix. K is going to be the brain regions, and then t is going to be the time series for each of those brain regions. We're going to go ahead and calculate a dynamic correlation, a dynamic Pearson correlation. So we're going to calculate a correlation between every single pair of nodes, so between A over K1, K2, K1, K3, K2, K3, et cetera. So we'll produce a K by K matrix. And then because these are dynamic correlations, we're going to also have it by T as well, because we're going to have a correlation at each time point as well. And B kind of shows how we calculate those dynamic correlations. In this case, we're using a Gaussian, but again, TimeCore we haven't allowed for a lot of different ways to calculate that dynamic correlation to calculate the dynamic correlation, not just a Gaussian kernel. And this is the heart of TimeCore. So once we go ahead and calculate that next higher order correlation, we produce that K by T matrix, so pretty big. We want to go ahead and project that back down to a K by T matrix, or the original size of the data. This way, our data only grows linearly and not exponentially, and this is what allows us to calculate those higher order correlations beyond first and second, really. Timecore is this, in the data I'm showing here, we use PCA for the data reduction, but again, Timecore, I have just implemented some new data reduction techniques like TSNE, UMAP, and sparse PCA, and those, we have some promising results using some different data reduction techniques as well. So that is a little overview of what Timecore is. So let's show you what we have done with Timecore. As some of you might be familiar with the Pyman data set out of the Yuri Hansen's lab. This was fMRI data collected while patients listened to 4 stories: an intact story, a paragraph scrambled story, a word scrambled story, and a rest story. And the rest are just used for the control. Here's an example of the word scrambled story. As you are reading this, notice the difficulty in understanding and visualizing what's happening and what's going on. We'll come back to this in a second. Here is a paragraph scrambled, or this is a sentence scrambled story to resemble a paragraph scrambled story that they would have listened to while getting their brain read. Again, it's a little bit easier to understand than the last one, but still very difficult to kind of visualize what's happening. And then finally, the intact version. Again, this is much easier to read. You can begin to visualize what you're reading as well, too. So then we went ahead and used cross-validation to train a cross-participant classifier to decode listening times. We trained classifiers by adding more higher-order correlations. So we started with just the 0th order correlations, and then we moved to 0th and 1st, and then 0th, 1st, and 2nd, and 0th, 1st, 2nd, and 3rd, et cetera, all the way up to 10th order correlations, which we got up to in this case. And by training these decoding models on different blends of these neural features, we can better understand which aspects of neural activity patterns are informative and important for those higher order cognition. And what we're decoding here is based just on the neural data, and we can predict when in the story someone is listening to. So that was kind of our final goal, is, hey, given your fMRI data, can we predict when in the story, at what time you're actually listening to? This means we're using a cross-participant decoding. So we're saying how similar is your brain compared to other people's brain that we have in the study as well. So again, this is another example of some stimulus-driven thought. First, I'm going to show you the decoding accuracy as a function of the number of orders in the correlation and the condition that the story was presented to them in. And just for a hypothesis, if it were the best decoding came from just the 0th order, so the raw activity patterns, we would see the best accuracy at 0th, and they would kind of taper off after, as adding these more higher order correlations would just lead to some noise and inaccuracy. Or we could also, or another hypothesis would be that, hey, as we add these more levels of interaction, we could decode better than the raw activity patterns, and we should see a spike up to a certain point and then kind of level off after that. And that's kind of what we see here. Just to quickly orient you with the results, again, the color is going to be what condition the story is in. Our x-axis is going to be what number of higher order correlation we used up to in the decoder. And then on the left is going to be the relative accuracy relative to chance. And because there was 300 time points in the time series, just to get the right answer by chance would just be 1 in 300. So that's the relative accuracy compared to chance. Then we see 2 things really emerge from this. The first one is that as the story is more temporally structured, so as the fidelity of the story increases, our relative accuracy of our decoding increases. And this is, again, a replication from Yuri Hansen's lab as well. And the second is that as the story is more structured, the higher order patterns become more important and informative. For example, in the intact story, we see the best decoding accuracy when we use up to the 2nd order correlations. And for the rest in the word story, we see the best decoding accuracy just using the raw activity patterns. Again, these data were all collected using PCA as our data reduction technique, but in some recent work that I've done, like in the last 2 or 3 weeks, I found upwards of 50% improvement on these accuracy scores using some different data reduction techniques, which unfortunately I didn't have enough time to put into the presentation for today. Next, we looked at the average dynamic correlations at each order, and we looked at which regions mediated these interaction patterns at each brain region. Then we ran a meta-analysis using neurosynth to find the top 5 terms associated with those brain regions, associated with the most active parts during the decoder. I'm going to draw your attention to what's in that black box there. These are going to be the words and processes associated with those first order correlations. As you can see, these processes are all kind of similar across the fidelity of the story. It kind of suggests maybe that regardless of listening condition, intact paragraph or word, we first have to, the things to do with low auditory sounds and auditory cortex in speech are going to be most used as we're trying to understand and take in what we're listening to. And then next, I'd like to draw your attention to what's in this black box, and these are going to be the higher order correlations of the word and paragraph. And while these stories are still pretty difficult to understand, we see additional involvement of some more semantic and speech processing centers. Again, suggesting that, hey, maybe we're trying to understand what we're reading and listening to even more. But what I think is the coolest part of this all is if we look at the 3rd and 4th order correlations of the intact story, and this kind of paints a different picture. This shows activity in the a lot of visual centers, the early visual, and primary visual. And this might reflect us, again, beginning to visualize that story, which some of you might experience when reading that intact story. To wrap things up, TimeCore is a Python toolbox that allows for the efficient higher order correlations of any time series data, not just fMRI data, as it projects the expanded matrix back down into the original matrix size, so our data only grows linearly and not exponentially. TimeCore was then used to analyze the PyMin data set, where we discovered that higher order interactions were reliably conserved across participants, and when tasks evoke even richer and deeper level processing, this was reflected in those higher order thoughts. And then using neurosynth decoding, we were able to find that higher orders of network interactions support higher levels of aspect and cognitive processes. I would like to thank everyone for your attention and for everyone for coming. I would like to give special thanks to Dr. Lucy Owen for allowing me to be here. And I'd like to give thanks to the University of Montana and the NSF for funding this research. Thank you.
I don't think we have any questions here. Any questions from the audience directly? Nope. I'm curious, you mentioned data reduction techniques and changes in the result. How much does it matter how you reduce it?
That's a good question. Like I said, so those accuracies are around like 25 to 30%. With different data reduction techniques, I've seen accuracy up to 50%, so that's like a big improvement and a big increase, so I think it matters quite a lot. So that, again, that's what we're currently doing right now, so I don't have a definite answer for you, but that's what we're working on in the future, and so we should have a definite answer in the upcoming months here.
Anything else? Okay, then we can go into the panel part.